All right, so welcome everyone back to 264A. This is our last lecture. It's been quite a journey doing this online. And today what I decided to do, instead of dedicating the lecture to one new topic, I'm actually going to talk about 4 different things. And these are topics that I wished we could have spent more time on. Some of them are things we mentioned in passing, and some of them are just follow up on things we did, so you can think of it as a wrap up. Now you have the ingredients for these topics, so you can pursue them on your own, but I wanted to give you an overview and point you to the important concepts there, so we have a more complete picture of what's going on. And we will augment the discussion with some papers that we're going to put in the description of the video for this lecture, so you can folks follow up on that. So we'll do these 4 topics. We'll spend a bit of time on each one of them, and you'd see they're going to be assorted from different places of the course. And then towards the end, we'll have some concluding remarks. So let's go ahead and see what these 4 topics are before we get started. All right, so here are the 4 topics. The first one will be basically a follow-up on the discussion we had last time, where we talked about arithmetic circuits for inference in probabilistic models. And the focus there was on using ACs for inference. And here we're going to say a number of things about using them for learning from data, which is a very important topic. And there we'll end up talking about, in particular, using them for model-based supervised learning. You can use them also for unsupervised learning, but this is more like how people use neural networks today. And then we'll end up talking about the representation of ACs using tensor graphs, which is something that has been happening recently, very, very important practically. These are the representations that are used for neural networks, and basically it could mean orders of magnitude in terms of difference in terms of efficiencies and speed up. We'll end up talking about an important topic of how do we exploit what we call unknown functional dependencies. We'll explain what that is. And then the second topic we're going to talk about is, which would be a briefer one, is how do we solve problems in the class PP to the PP complete using tractable circuits. Now, we focused quite a bit on solving problems that are MP complete and that PP complete. The PP complete ones are, for example, computing marginals and probabilistic reasoning and so on. But we also talked about NP to the PP and PP to the PP, but we didn't say much about the last 2 classes. And again, you do have the ingredients for this. So we're going to just make a couple of remarks there about how you can use what we talked about to do that, so that we just complete the picture. And then the other topic I'm going to talk about is this notion of graph abstractions of knowledge bases. We did mention throughout the course that you can sometimes give various guarantees on things. For example, when you're compiling CNFs to various types of tractable circuits, and as you'd see that a lot of these guarantees are based on taking your input and abstracting it into some kind of a graph. And there are different types of graph abstractions. And then there are properties of these graphs that people in computer theory have studied extensively, which can be used to actually offer these guarantees. So we'll basically paint this picture for you. It's pretty involved, but you will get really the game there and the main concept. So if you want to follow up, it will be pretty easy to do that. And the final topic I want to talk about is this notion of auxiliary variables. This is a very important technique from both a practical and theoretical point of view. And roughly, this is when you take your knowledge base and before you operate on it, you augment it by adding auxiliary variables that were not part of the input. And there are different reasons why you may want to do that. From a practical point of view, people do that so that you can think of it, they make whatever they want to do easier, and they call that pre-processing, but it actually is something that can be looked at from theoretical angles, and it could have implications on complexity. There we'll talk about two main applications. One of them is something called extended resolution, which is an extension of our resolution inference rule that can lead to exponential speedups. And then we look at another application from compiling tractable circuits. Now, again, very, very important, and you'd get the gist of it, and you'd get really some core insights there about what's going on. We'll start first with the use of arithmetic circuits for learning, in particular supervised learning. And there, again, what we'll be doing is pointing to a number of concepts, and a lot of this is recent, what I'm going to be talking about. Now, when I say recent, that's the last year. So if you look at the pipeline that we built last time, where we basically said, I want to answer queries about a probabilistic model like a Bayesian network. And the way I want to do it is by compiling it into what we call an arithmetic circuit so that I can do linear passes on this guy and then answer queries on that guy like MPE and marginals. And the pipeline took the model, wrote a Boolean formula, compiled it into a Boolean circuit of appropriate type, and then extracted an arithmetic circuit. Now, this is an inference story. This is where we're using tractable circuit to basically do inference on a model that we already have. But you can also use this in a learning context, and in particular, when you're learning the parameters of this model from data. So the story that we gave assumes you have this model fully, but sometimes you don't. You may know the structure of the Bayesian network, but not its parameters. And then you can use this pipeline actually to do learning. And that turned out to be an interesting story. Now, when you talk about learning, there's two kinds of learnings. There's learning the parameters, and you can go the extreme way of just really learning the whole thing from data. Now, that's another area, and it's outside the scope what we're going to be talking about. But let's look at it from this angle. And again, this would be a story to allow us to insert a number of key concepts and recent developments that you need to be aware of. Now, remember this picture from last time. What we had here is a model, a Bayesian network. And if you remember, we talked about two types of encodings of this Bayesian network into a Boolean formula that then we used to extract, compile, and then extract an arithmetic circuit. There was this and that. The first encoding we gave didn't capture the values of these particular parameters, and then it generated a circuit that looks like this. Where, as you can see, the inputs are either these indicator variables that we use to capture evidence, or these parameters, thetas, which effectively come from this guy. And the point we made here is this will work for any values of these guys. Once you know these guys, you can plug them in and you can use this. But that came at the expense of being not very efficient. And then the other encoding, where we captured the values of these parameters and generated a circuit that was in a way more efficient, but specific to these parameters. Now, these are two extremes. What happens is that sometimes you do know some of these parameters and you don't know others, right? So you're building a model for a situation, and you may know that basically B is a function of A, as shown here, but you really may not know how C is related to A. You don't know these probabilities, or you may not know the prior on A. So in that case, you have a situation that's somewhere in between. And you can generate a circuit in which some of the parameters are known and some of the others are not. And then you won't be ready to do inference at that point. So what you need to do is first learning. You want to learn those missing parameters from data, and then you have a circuit that's ready for inference. Now, in the rest of the discussion, we will use a particular term to refer to those parameters that you know. We're going to call that background knowledge, right? So we have a situation where you may know some of the parameters and may not know others. And the ones that you know, we'll call that background knowledge, right? So if you knew this, for example, we would say that this functional dependency is background knowledge. Another concept that will come up, which is another type of background knowledge that is not exactly known parameters, but pretty important practically. And this has been identified very recently during the last year. And let me explain what that is. That is what we will call unknown functional dependency. Now, I think we talked last time about what a functional dependency is. So let me explain what is it to have an unknown functional dependency. Now, functional dependency is when you have a CPT like this. So in this particular case, let's say you have the variable x and it has a single, or it has this child y. So y has a single parent x. And now I'm specifying this distribution over y given x. As mentioned, you have two distribution here, right? One for x0 and one for x1. And you can say 0, 1, 1, 0. What does this mean? This means that this table or this conditional probability table is really capturing a function. It's saying that once you tell me the state of x, I know for sure what the state of y is. And here's the function. x0 goes to y1, x1 goes to y0. This is what we call a functional dependency. So it's a stronger version of having 0, 1 parameters, because these 0, 1 parameters are pinning the value of the node given the state of the parents. Now, this functional dependency could be different. So this is another functional dependency for y being dependent on x, right? Different distributions or deterministic distributions. And in this case, the function maps x0 to y0 and x1 to y1. Okay. Now, here's an interesting concept. Sometimes I know that y is a function of x, but I do not know what that function is. All right? So we may know that y is a function of x. That is, we have the situation, but may not know the identity of that function x. And I'll give you examples later where this come up. There is a very major context where this comes up. Recently, we found a way to utilize this kind of background knowledge. Now, remember, now we have two types of background knowledge when we talk about functional dependency. I'll tell you y is a function of x, and of course you could in general have more parents there, so you may have z. So y is a function of x and z, and I give you that function by specifying the 0 1 parameters. And another level of knowledge, which is weaker, where I will tell you y is a function of its parents, but I don't know what that function is. And interestingly enough, you can utilize that when compiling circuits, and it could lead to exponential difference. Exponential when you utilize that information, all right? So more broadly, you can think of this notion of background knowledge here as what we know about the parameters, and that could be knowing their actual values or knowing something more abstract about them like I've shown here. All right, now let's keep going with this story and tell you a little bit more about compiling into arithmetic circuits. So in the pipeline that we've shown here, basically we learned or compiled a circuit for the whole Bayesian network, which can be used to answer different type of queries. You can think of this as a compilation of the model. But what you can also do is compile a particular query. What does that mean? Here's a Bayesian network. And then I'm come and tell you, listen, I'm going to use this in a very specific way. I'm going to have evidence on A and C. This is my input, and I'm interested in the posterior on that guy. So let's say in a diagnosis application, you may have some symptoms and you're after a particular disease, right? And you want the distribution on this because perhaps you want to do classification. Does the person have the disease or not? In that case, you can compile an arithmetic circuit that's dedicated for that task. So you can think of it as a query-based AC. And in this case, it looks like that. So what's happening here? What's happening is, look at the output. The output now is not just one number. We have two numbers which represent the distribution on this. These are all binary variables. You know what the inputs are. The inputs in this case are just lambdas only for A and C. So these could be used to capture the evidence on my input variables A and C. And then the rest of the parameters, you see what these guys are. They come from the Bayesian network. And sometimes, because this is a query-oriented AC, not every parameter of the Bayesian network may end up showing up in this circuit, only those that are relevant. Now, the point is, when you have something like this, and you try to train it from data by trying to figure out what are the values of these, you can do this in what we call a supervised manner, meaning I can give you pairs of inputs, outputs, and this is what we call labeled data. So you may have patients and say when they had this and that, they did have the disease, they did not have the disease, right? So you have these input-output pairs, and then you can try to learn these parameters using gradient descent. So this is similar to what happens in neural networks. In neural networks, the most common way of using them is in this fashion, where you select a certain network architecture, and then you have labeled data, and then you train them. You can do the same thing in this particular case. In a sense, you want to think of this as like a neural network, but instead of being handcrafted, it is synthesized automatically from a model. And because of this, you can offer a lot of guarantees on what was learned because of what you may know about the model and so on. And when you're setting it up this way, this notion of background knowledge that I may have, which, as we discussed, is some knowledge about the parameters, can be easily integrated. So some of these may actually be known because of your background knowledge, and then you only have to learn the rest. And it is pretty attractive. When you look at it from the context of neural networks, one of the biggest problems people have with neural networks is, how do I augment them with background knowledge? Because those architectures, they do well on certain problems, but the wires and the neurons, we don't know what they mean. So if I have some background knowledge beyond the data, it's not as easy to integrate that in the neural network. In a situation like this, that's basically straightforward because every node here has a meaning. In fact, you can even trace the internal nodes of the AC and think about what particular probabilistic computations they're doing. All right, so that's another use of these circuits. You compile them from models, and some parts of them are not known, particularly the parameters, and learn them from data. Now, some of the recent developments on this front, and I want to mention two of them you need to be aware of because they're big deals. One of them is this notion of, how do I represent this guy? So traditionally, these have been represented like this, graphs with nodes that represent additions, multiplications, and so on. But if you look at these circuits, you'll see a lot of their operations can be done in parallel, right? So these two guys do not depend on each other, so I can do them in parallel. These four multiplications actually do not depend on each other, so they can be done in parallel. And one of the main technologies today to try to capitalize on this is what people call tensor-based computations or tensor graphs. So there was a recent algorithm just from this year which compiles these models into arithmetic circuits in the form of what's known as tensor graphs. Now, let me just briefly mention this. Some of you may know this if you've been playing with neural networks. We've been playing with tools like TensorFlow and PyTorch and so on. That's the bread and butter. That's the basic representation people use for neural networks. But what you can think of this as simply trying to do these kind of operations in bulk. If you look up tensors on the web, you will probably be pointed to tensors in physics. It's a fancy name for a multidimensional array. And why would you call multidimensional array tensors? That's another story. But typically, when you say tensor, it's not just a multidimensional array. It usually means that I'm doing operations on these multidimensional array in a parallelized fashion. When you take two multidimensional arrays and let's say you do pointwise multiplication or you do something called sum reduce, where you're adding some rows in those arrays. All of that can be easily parallelized. So when you're talking about tensors, you're talking about multidimensional arrays that are with parallelized implementations. And this kind of parallelism, you don't even need sophisticated hardware for that. Even on your CPUs these days, on your laptops, they can take advantage of that and basically offer you certain types of parallelism. So when you take something like this and represent it as a tensor graph, you can think of these blocks as these tensors. And when you have this and that, you're doing a tensor operation. So perhaps this is pointwise multiplication of these two guys. Then it's like doing this, but doing these operations in bulk and in parallel. Doing this in the straightforward way, you would do it if you just did the classical data structures course where you present this as a list of operations and you walk through the list doing multiplication and addition, versus doing it in a tensor graph. You can easily see orders of magnitude, all right? So going from this to that in some of the applications could be waiting days versus minutes. So it's a really big deal. And even though you have many different kind of tensor operations, that is operations on multidimensional arrays, one of the most optimized is matrix multiplication, where you view the two multidimensional arrays as matrices and just do matrix multiplication like you know it from algebra. So if you want to map something into a tensor graph, people want typically to map that into matrix multiplication operations. And this latest algorithm will give you a pointer to that. Indeed compiles a tensor graph for the AC, which is mostly made up of matrix multiplications, which is a very big deal, all right? So you need to be aware of that. The compilation algorithm uses different techniques than what we studied, but you need to be aware of it, all right? And that is very, very significant computation. Now, this is a relatively recent area. Only the last few years, people start doing this. And what technique you use to do this also depends. Am I compiling the AC from a model like we're doing here? This algorithm is dedicated to that. But sometimes you're handcrafting this or learning from data. That ends up being another ordeal. But it's pretty exciting that this very enabling technologies that have been critical for neural networks is now available for these circuit types. And I'm going to give you a concrete example, by the way, of this, just so that you get to see a more concrete usage. This algorithm that I mentioned, which basically goes from graphical model to NAC in the form of a tensor graph, can exploit unknown functional dependencies, meaning you can come and tell me, by the way, I know that C is a function of A, but I don't know what that function is. That algorithm knows how to take advantage of that and can generate exponentially smaller ACs in that particular case. Let's take just a quick example of a context where this appears. This is an example where the idea was to look at images like these and identify the objects. So we're trying to identify rectangles or these 7-segment digits when you have some noise. Let's focus on the rectangles, right? And here you may want to look at an image and predict whether the rectangle is tall or wide, or predict what is the upper left corner, what is the row and column of that upper left corner, or what is its width or height. Here's the simple Bayesian network that does that. Okay, this happens to be synthetic image recognition or object recognition, and the intention was that it's easy to come up with a model in this case, a Bayesian network, right? So every rectangle has the upper left corner has a row and a column. It has a height, it has a width, it has a shape. In this case, it's just either tall or wide. And what this means is whether the rectangle will render in row I. And as you can see, that is a function of the row of the upper left corner and the height. So if you tell me what is the row of this point and how high it is, I can determine for every row whether the rectangle will render there or not. That's a function of these two guys. And this is similar to the column. Would the rectangle render in column J? That depends on the width of rectangle and that first column here of this upper left corner, all right? And this is the pixel, whether the rectangle will render in pixel ij. In general, this is also a function of these two guys, but you may not want to have this as a function because you may have noise, right? So, but this is a setup where you may want to do a query-oriented AC, compile a query-oriented AC. For example, suppose that someone went to these images, let's say the rectangle ones, and labeled them, and he said, this is tall. Okay, this happens to be tall, and maybe label something as wide. So your data will be an image, which is the pixel values, a whole bunch of values there, and the shape, tall, wide. And then what you do in that case, you go ahead and say, okay, let me compile an AC. When you want to compile an AC for a particular query, you have to tell me what's your input, what's your output. So in this case, what would be the input? Can you tell me which variables in the Bayesian network should be designated as the input, the ones I'm collecting evidence on, and which is the output? What I'm trying to do is build an AC and train it so that if I give it an image like this, it comes back and says, yeah, this is a tall rectangle. So in this case, which variables would be the input? Those would be the pixel values, right? So you have n square of these. The pixel values would be the input, and the output variable will be the shape. So we'll say compile an AC that will take the values of the pixels and compute the posterior on the shape variable. All right. Now, just quickly before we leave this topic, here you'll see, for example, when you do this compilation, you may have different types of background knowledge. So sometimes you may know the CPTs of certain variables. So in this case, I know that this is a function. In fact, in this case, I also know what the function is. You may not know what is the distribution over rows and columns because you don't know where do the rectangles tend to appear. You may not know their heights. You may not know their widths. So here you have a mix of parameters that you don't know and some that you do know. And interestingly enough, just to give you a sense of what's going on here, and the impact of knowing some of the parameters. So these were an experiment. This is for the digits model, which we're not showing. It's way more complicated than the rectangle model. Three things were compared: an AC that was compiled from this structure without assuming any knowledge of the parameters, and another AC that was compiled where we use the values of some of the parameters that we know, particularly that this is a function of these two guys, and this is a neural network. And the idea was to see to what extent knowing things affect the amount of data you need to train. And you can see eventually they catch up to each other, right? So at least this guy and that guy, after 8,000 labeled images, they end up being very good. This guy needs a little bit more data, and you can imagine this is learning more than this guy, right? This is already being boosted by being told some of the values of these parameters. And the nice thing here is, I mean, look at 250 images, labeled images. This guy is already done, right? And this is way behind, this is behind. The nice thing about these representations, if you want to think about it from the viewpoint of potentially an alternative to neural network, is it is easy to encode background knowledge into these things. Of course, the hard part about them is coming up with the models. These were toy problems where it's easy to come up with the models. The main challenge usually is for a lot of tasks, we don't know how to build the models. And neural networks do not need that, right? They have found certain architectures that work generally for certain problems. Let me just mention one last or couple of remarks on the subject of unknown functional dependency. I want to mention a class of models that have been subjected to extensive studies where this come up. And this is when we're talking about the world of causality. There is a special type of Bayesian networks that are known as structural causal models. They're just Bayesian networks with some additional assumptions on them. And in these kind of models, the root variables are called exogenous variables, and the non-roots like X, Y, Z, W, U here, these are called endogenous variables. And in these kind of models, the assumption is all of these variables are functional, meaning X is a function of its parent. Y is a function of this guy, and that guy. This W is a function of these three. And the only uncertainty or probabilities you have are on the root variables, right? So this is an example where pretty much every internal node, every non-root node is a function. And when people use these models to do causal analysis, or what people call causal inference, I know that these guys are functions of their parents, but I don't know what these functions are, right? So typically you don't know what the parameters, and then you try to make causal inferences based on that. So this is like one of these major areas where this notion of unknown functional dependencies come up. So someone is asking, we also don't know the distributions. Yes, we also don't know the distributions. But then you can do a lot of other things just based on the causal graph that you have here, even though you may not know the distributions and even though you may not know the functions. So it's pretty interesting subject, but that's another ordeal, another area. I just want to end this segment just to give you a sense about how significant this is. We'll post the paper for this. This is recent from this year. Two things I want to highlight on this. These are example Bayesian networks with different sizes, but I want you to focus on two things. One of them is this. This is trying to show two things. One is what happens if you exploit versus not exploit unknown functional dependencies. And this is a busy table. It's hard to read what's going on, but I just want you to focus on one thing. For each one of these cells, you need to be exponential in this if you did not exploit functional dependencies. And after exploiting these functional dependencies, you need to be exponential only in that. Now, that's a big deal. You can go all the way here. This is impossible now, right? You cannot do this. And that drops down to this, so it becomes feasible. These are ACs that are represented as tensor graphs, and look at their evaluation time. This is actually on a CPU, right? Almost 100 million nodes, 76 milliseconds, right? This is basically pretty significant, very, very significant. And that's because of the tensor graph representation as opposed to the classical representations. All right, so I hope that this gives you an idea. And just to wrap up here again, we're not only compiling these ACs from models, you can learn them from data. And when learning from data, there is different degrees. You can learn just the parameters from data. So you have something like a causal structure. You compile an AC, learn the parameters from data. And people now go all the way to learning the whole thing from data. That's another game. And as I mentioned, even sometimes people can't craft the structure of an AC and then learn the parameters, as opposed to compiling from a model. Most of what we talked about here is geared towards compiling from models. And that's basically it. So we're now ready to go to the next topic that we're going to mention today, which is going to be much shorter. And this is the subject of solving MAJ-MAJ-SAT using tractable circuits. And these are PP to the PP complete problems, which again will be a short topic because you already know all of the ingredients. But before I do this, any questions so far? All right, so good. And we'll probably deal with also with the questions as usual towards the very end. Now, as you know, we talked about these four major complexity classes, NP, PP, NP to the PP, and PP to the PP. This was the basically hardest of these four. And if you remember what that problem was, it was simply that if you have a knowledge base or a Boolean function over two sets of variables, we partition the variables into X and Y, then the MAJ-MAJ-SAT is asking, is there a majority of instantiations X under which the majority of instantiation Y satisfy this, right? So there's an exponential number of instantiations here, an exponential number there. I want you to go over these basically one by one, let's say, and for each one of them, condition the function on that, and then ask, are they, because this now is a function over only the Y variables, and ask, do the majority of Y satisfy that, okay? That's basically what MAJ-MAJ said. And of course, this is the decision version. This is the simple prototypical problem for this class. It is PP to the PP complete, means it represents this class and it's the hardest in that class. If you know how to do this, you know how to do other things, like we talked about the same decision probability, which has numbers and look way more complex than this and look more applicable. This is when we are using a Bayesian network like this to do classification based on some evidence. And then I made a decision based on this posterior that this patient is not pregnant. But then I tell you, okay, what would happen to your decision if I were to learn these two guys? And the SDP in this case tells you, oh, there is 78.7 chance you will still make the same decision even after collecting that. Now, this looks very different than this, but they're not actually. And in fact, you can see the split of variables X and Y here showing up there, because now I have two different set of variables. I have these, which are special. I'm going to have only a few slides on this. And we'll give you a paper on this, and you'll see the reduction. So how the concept I'm going to mention now, which you already know, by the way, I'm just going to make pointers to things we studied, how it can be used to do this as well, not just that, okay? And the basic thing is, what kind of a circuit should I use? Because when we looked at other kind of questions like SAT and MAJ-SAT or sharp SAT or weighted model counting, we just pointed to a circuit type, said, take your knowledge base, compile it to that kind of a circuit type, and then you can solve that problem in linear time. Well, there is such a thing here also. And you know that circuit type, but you have to use it in a particular way. If you take this guy and compile it into a certain circuit type, then you can do this in linear time. And this is SDDs, sentential decision diagrams, or SDD circuits, but with one thing that you have to pay attention to. If you remember, SDD circuits have to conform to a Vtree structure. A Vtree, which is this binary, full binary tree where the leaves are the variables of the Boolean function. So in the sense that you can see the numberings of the Vtree nodes and the numbering of the decision nodes in the SDD, in the sense that we would say that this guy is normalized for that. In the sense, if you look at this decision node, you look at the primes and the subs, you're going to find that the primes have their variables in this guy and the subs have their variables in that. And similarly, all of these primes here are normalized for that node, and all of these subs here are normalized for that node. So you cannot construct an SDD without first constructing a Vtree. And it turns out that if you use a particular Vtree when constructing the SDD, then you can use the SDD to do MAJ-MAJ-SAT in linear time. And similarly, you can use it to do other kind of computations like the SDP, same decision probability in linear time. So the question now you're going to tell me, oh, wait a minute, so what kind of a Vtree we're talking about? Well, let's see. You need now what we call an X-constrained Vtree and therefore X-constrained SDD. But if your Boolean function, fxy, is represented by an X-constrained SDD, then MAJ-MAJ-SAT can be solved in linear time. So we just have to explain what this guy is. So you can't use any SDD circuit. You have to use an SDD circuit that is constructed while having in mind this split of the variables. And we've seen this concept before, but under a different name. And now we'll use the original name. So let's say in this case, my function is over the variables A, B, C, D. And this is the split of the variable xy. That means I'm looking for whether the majority of these instantiations are such that under each one of them, the majority of these instantiations satisfy. So here's an example Vtree in this particular case. Remember, a Vtree in general is just a binary tree. You just want to make sure that the leaves are in one-to-one correspondence with your variable. So this is one of them. But this one happens not to be just any Vtree. It ends up being what we will call an X-constrained Vtree. And what does that mean? That means it must have a special node V that appears on the rightmost path, this rightmost path here. And the set of variables outside it are exactly X. So actually, this guy does have that. Here's the node. Look at this node. It is on the rightmost path. And if you look at the variables outside this node, they're CD, which is my X, which means basically the variables under it are the Y variables, A, B, E. Now, not every Vtree will have this property. I can show you Vtrees over these 5 variables that does not have that kind of a node. But no, you want one that has that kind of a node. And that will be called an X-constrained Vtree. Now, we've seen this before under the name of conditional Vtrees, and we used it when we talked about conditional PSDDs. This usage came before this. So initially they were called X-constrained and used in this particular context. This is in 2016, and this came in 2018 where the same concept was used, but they were referred to as conditional Vtrees to match this notion here. So an SDD is X-constrained if and only if it is normalized for an X-constrained Vtree. We know what's going on now, okay? Now, the algorithm itself, if you do have an SDD that is conforming to an X-constrained V3, the algorithm for computing MAJ-MAJ-SAT ends up being very simple, a single pass. I'm just going to flash the code on the next slide just to probably encourage you to maybe check it out, because it's pretty simple. And then I'll just make one more comment on this. And then that would be basically the part that we need to do here. Now, this is the code, okay? And a lot of it is just, setup, right? It's just really doing a pass over the SDD node children before parents and doing simple computations. Okay, we're not going to do this. But that leaves the question of how do I get an X-constrained V3? And one way of doing it is to first just compile or come up with any V3 and compile an SDD without worrying about being X-constrained, all right? So you may end up compiling your SDD successfully with respect to this guy. Now, this guy is not X-constrained. In this case, X is CD. And if you look at this guy, the only two nodes, internal nodes that are on the rightmost path are these guys, and none of them satisfy the condition that we want. So you have your SDD with respect to this. And then you can do V3 search, as we explained before, by modifying this V3 and trying to get it so that it is X-constrained. Now, this is X-constrained in this case. This is XCD. Here's a rightmost node, and CD happens to be precisely those that are outside, okay? You want to think about it that way, or you want to think that the Y are exactly the guys below it. And if you end up starting with an SDD with respect to that, and then you search and you're done. But you may not stop there. Now, this is another X-constrained V3. Look at this guy here. That's also an X-constrained. It's on the rightmost path, and the variables outside that are CD, which is mine. So either of these would work. Now, one of them may be better than the other, but the one thing you should see here is because of insistence on X-constrained V3s, that basically means that my SDD could be bigger than it could have been if I were to use an arbitrary V3. Now, that should not be too surprising, because now you're trying to use it to solve something pretty difficult, PP to the PP complete problem. But you see what's going on here. You already have all of the ingredients. You know what a V3 is. You know the operations on V3s. Remember rotations and swaps. And you know systems that actually do this search for you. You just have to modify the search algorithm so it looks for one of these guys. And you've got all of the ingredients. And now you see how you can use this to solve very difficult problems. Now, the SDP and MAJ-MAJ-SAT are kind of exemplary of expectations. So not now talking about probabilities, we're talking about expectations, probabilities of probabilities, which is pretty useful practically. And here you see how it works. All right, so I just want to make sure that we close this gap, and for you to see that even though we did not dedicate a lecture to the subject, you pretty much know the ingredients, and you can play this game pretty easily based on what you already know. All right, folks, so this basically is the first two topics we want to talk about today. We have two more. I expect they will take less time than the first two, but perhaps we can take our 10-minute break now and resume at 11 with the remaining two talks. So let's do that. Thank you.